Okay, good morning. Hello, Discrete Math. We are making a video. I'm making a video right now going over the homework from page 232 of Gossett. This was the homework that I assigned to do during the asynchronous learning week. So that was like a whole 14 days ago, I believe. Gosh. So yeah, this video really should have been made like a week ago, and I have been putting it off for a week. Why have I been putting it off? Because it's really hard. We're gonna solve a whole bunch of counting problems. This video is, hopefully it's only gonna take an hour, but man, it could take like 2 hours because even live in class, where I have 25 people all thinking out loud and sharing their thoughts extremely quickly, it takes a long time to discuss these problems, especially if you want to look at them from every possible angle, if you want to consider trying to understand the problem, considering multiple interpretations, and talking about all the ways to solve the problem correctly, the ways to solve the problem incorrectly, why the incorrect solutions don't work, why the different correct solutions do work. So it's very time consuming. I think it's a very valuable and important part of learning, so hopefully everyone's watching this video. It's crazy to not do this live because it's a basic kind of live lesson from Discrete Math, especially with many smart people all having put in a lot of effort and thinking about the problems in different ways and all sharing their solutions, and the whole class together kind of listening to the solutions and deciding whether they make sense or not. So I am not an expert on these problems. I can do all these problems, but it's very helpful to have other smart people in the room with you to talk these things out with. So that's why I've been procrastinating doing this video. And I'm probably going to have to do it in pieces. Let's begin. The very first problem, so where are we? We learned some basic counting problems, or I should say 3 weeks ago or something, we learned basic techniques. And this was to some extent just a refresher from things that you learn in pre-calc, combinations, permutations, and then some new things like the stars and bars method. Then we did a homework assignment. There was a video for that, and then there was at the end of that video there was a kind of a lesson on the multinomial counting theorem, as Gossett calls it, and then there was a second set of homework problems. I consider these to be way more difficult, and they're way more difficult than anything we did in pre-calc C. And what's typical of them is it's not just one simple little solution. You have to sort of use all of the various techniques in many ways. I think these are hard. They're still easier than the kinds of problems that you do if you do a lot of a math team. So once again, those people who do a lot of competition math have done millions of these problems before and gotten very good at them. So maybe you didn't find these that hard. Anyway, I don't do competition math, so I find these pretty hard. Let's go. The very first problem on page 232, number 1, is already like incredibly difficult. Not so difficult to solve, but interesting in that there are many different ways to solve it. So let's begin. I have a screenshot on my phone from what we did last year. I was so happy with this that I took a picture of the whiteboard in room 317 or something like that. And or 315, I guess. That was on February 28th, 2020. So we're 3 weeks behind. Okay, Gossett, what do you got? A boy needs to eat breakfast and lunch, practice piano, mow the lawn, and read a book today. In how many ways can he arrange these activities if breakfast must occur before lunch and at least one other activity must separate the meals? Okay, I like what Gossett's doing here because this is sort of a thematic callback to a previous problem that we talked about when in the other video from 2 weeks ago, which is that, do you just call the first meal of the day breakfast, or do you define breakfast by pancake related or something? And here we are taking the interpretation in which whichever meal comes first, we're calling that breakfast. That's one way of interpreting this problem. So what's this boy going to do? He's going to have 2 meals, breakfast and lunch. So maybe I'll just write that down. There's finally getting started with this video. There are 2 meals. There's breakfast and lunch, and then breakfast has to come before lunch. So in other words, he's going to eat 2 meals, and we're going to call the first one breakfast. And you're not going to... Oh, and then he's 3 more activities for the day. What are the 3 activities? He's going to practice piano, he's going to mow the lawn, and he's going to read a book. Okay, so there are sort of these 2 meals, and the meals are kind of separate in some sort of way from the 3 other activities, which are going to occur in some ways between the meals. And so we want to consider every possible way of organizing these 3 activities. Okay, that would be 5 factorial if there were no restrictions, but in fact there are 2 restrictions, which is that breakfast comes before lunch, and also you can't have lunch come immediately after breakfast. You gotta insert some sort of activity between meal times. Okay, how are we going to do this? I'm going to solve this problem in 7 ways. Okay, ready? Here is the first method. This is, in some ways, perhaps the simplest method, and maybe the method that you would have thought of first. This is what I thought of. I just did some casework. I said, okay, well, look, these numbers are pretty small, so let's just go through the various cases. There is the case in which he has breakfast right at the beginning of the day. So let's go 1, 2, 3, 4, 5, 6, something like that. So there's the case in which he has breakfast right at the beginning of the day. Well, if that's true, then when can lunch be? Well, it can't be next, but it could be any one of the other 4 spots. So lunch, 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 lunch. So I have 4 choices for where lunch will then go. And okay, once I've placed lunch, then the 3 remaining activities are free to occur in any spot whatsoever. And so on the case in which breakfast comes first, there are 4 choices for where to put lunch. And then after that, there are 3 factorial ways to arrange the 3 remaining non-meal activities into the 3 free spots. Okay, then there is the case in which breakfast doesn't come first, but in fact comes second. So let me just So if breakfast comes second, then how many choices are there for lunch? Well, lunch can't come immediately after breakfast, so then there are 3 choices for where lunch can go. And then once I've decided where breakfast and lunch are, then there are just 3 factorial ways to arrange the 3 non-meal activities into the 3 free spots. Okay, how many more cases are there to consider? Well, not so many, because if breakfast doesn't come first and doesn't come second, then I claim it must come third, because, well, let's see. No, I guess it doesn't have to come third. What am I talking about here? Breakfast must become... Oh, do I like have an extra spot? 1, 2, 3, 4, 5, 6, 1, 2, 3... No, oh my gosh. This is just a bunch of total garbage. That's so embarrassing, almost considering starting over the whole video. I just miscounted to 5. There are 5 activities. Okay, so scratch everything I just said, or almost everything I just said. The numbers were all wrong. The logic was okay, but I just counted to 6 instead of 5. There are only 5 activities total. So if breakfast comes first, then there are 3 spots in which lunch may occur. Essentially not second. Lunch can occur either in the 3, 4, or 5 position. And now, having chosen where lunch is, there are 3 factorial ways to fill in the 3 remaining non-meal activities. And then in the second case where breakfast comes at second, well, lunch can come third, so there are 2 choices for lunch. And then, once I decide where lunch is, there are 3 factorial ways to fill in the 3 remaining activities. And the third case, which is the final case, is the case in which breakfast comes third. And if breakfast comes third, then since lunch can't come immediately after breakfast, lunch can't come fourth. So there's really only 1 choice for where lunch goes. It must go in the 5th spot. And so there's really only one choice to decide where lunch is. And then there are 3 factorial ways to do the rest. Okay, so by casework, it really wasn't too bad. There were just sort of 3 cases. I partitioned the set of possible schedules by the position of breakfast, whether breakfast comes first, second, or third, and I just add this up. Well, I get 6 times 3 factorial, and 3 factorial is 6, and so the answer to this problem is 36. Okay, so hopefully you got that, because solving the problem maybe is not so hard. So let's consider, was there another way? Well, I'm just following the exact order from last year. This is not necessarily the most reasonable order. This is just the order that occurred to the people in the class. I called them one at a time and I said, okay, share what you did. And someone said, okay, I got a new method, and I'm trying to reconstruct this from 13 months ago based on my crappy little pictures because I didn't write anything down on the board. But it seems as if someone else took a different approach. So in method number 2, instead of thinking of the 6 activities, well, instead of thinking of there as being 5 fixed spots, and now we are going to insert the activities into those spots based on the order in which they occur, I now think more sort of flexibly, or just differently. Let's imagine that breakfast and lunch are some kinds of like pivots or something. And, well, if breakfast must come before lunch, and there must be something in between breakfast and lunch, then let's just now place all the things in between. So this is maybe kind of almost like a worse method because there's even more casework, but it's a different method. So let's talk about it. Basically, having now fixed breakfast and lunch sort of with respect to each other, now let's just fill in activities in between breakfast and lunch. And, well, anywhere between 0, 1, and 2 activities can occur before breakfast. But some activity must come between breakfast and lunch, and maybe some activities come after. So okay, so basically, I guess what's the way to do this? Yeah, here's the way to do it. It's we partition by the number of activities that occur between breakfast and lunch, and there must be at least one activity between breakfast and lunch. And okay, if one activity occurs between breakfast and lunch and there are 3 activities, then perhaps 2. This chart makes now more sense to me as I'm looking at this. Perhaps, or maybe we'll start with 0. So no activities could occur between breakfast and lunch. Sorry, no activities could occur before breakfast. In which case, if there's 1 activity between breakfast and lunch, then there must be 2 activities after lunch. On the other hand, there could be 1 activity before breakfast. And if there's 1 activity before breakfast and 1 activity between breakfast and lunch, then there will be definitely 1 activity after lunch. Okay, then there's also the possibility, and this is now casework within the case in which there's 1 activity between breakfast and lunch. There could be as many as 2 activities before breakfast, in which case there will be no activities after lunch, because there are only 3 total activities. Yeah, this is making total sense. Okay, now consider, so that completes the case in which there's precisely 1 activity between breakfast and lunch. Could there be 2 activities between breakfast and lunch? Yes. And then there could be no activities before breakfast, and then there would be 1 activity after. Or if there are 2 activities between breakfast and lunch, there could be 1 activity before breakfast, in which case there would be no activities after lunch. And that completes the case in which there are 2 activities precisely between breakfast and lunch. Well, what else is left? There could be as many as 3 activities between breakfast and lunch, in which case there would be no activities before breakfast and no activities after lunch. And so what have we just done here? We've just done 6 full cases, and these 6 cases count now the all possible ways of sort of distributing the activities, by number of activity into the 3 sort of spots. So I'm sort of thinking of there's being really just 3 spots. There's the before breakfast spot, the between breakfast and lunch spot, and the after lunch spot. And since there must be at least 1 activity in between breakfast and lunch, then there are either going to be 1, 2, or 3 activities. Okay, I think this makes total sense. And well, for each of the rows in this little chart, I still now have 3 factorial ways of deciding, playing piano, mowing the lawn, reading a book, the order in which I do those 3 non-meal activities. And so there are 3 factorial ways, there are 3 factorial schedules for each row of this chart. There are 6 rows in this chart. And so once again, we get 6 times 3 factorial as my answer. All right, so that's method number 2. Method number 3 is kind of like advanced or something. Let's see if I remember this. I was preparing a little bit before class. Method number 3 is essentially stars and bars. But stars and bars in a weird kind of way in which, look, if breakfast must come before lunch, then you can think of breakfast and lunch, the meals, as kind of being like bars or something. And so, okay, so let's just kind of do that. Let's make a sort of a bar or whatever, and let's make another bar, and let's agree that these bars, I don't know why I'm drawing them like this. Let's not do that. Let's agree that these bars are going to represent breakfast and lunch in a kind of a weird way that's hard to explain. And now, this is in some ways it is a follow-up to the previous method, because in the previous method, that's what we did, right? We considered breakfast and lunch as being kind of fixed in place now, and we distribute the activities in between amongst those two fixed pillars. So it's actually reasonable. What we're searching for now is a way that's a little bit more principled. Is essentially like a more intellectual version of method 2, in which we're not just blindly going through the cases, because this would get way harder if the numbers got bigger. So is there some way to do this? Well, yeah, because I have essentially 3 activities. Think of my activities now as being stars, and I'm going to disperse the activities amongst the bars. And so actually, without the requirement that there be an activity between breakfast and lunch, this would now be very easy, right? Because then it would just be pure stars and bars. Distribute the 3 activities to the 3 spots. What are the 3 spots? The between breakfast spot, the before breakfast spot, the between breakfast and lunch spot, and the after lunch spot are the sort of 3 containers, so to speak, and I'm distributing stars to those 3 containers. How many stars? Well, 3 stars in total, because there are 3 activities, and I may distribute the stars in any number. I can put them all before breakfast, I can put them all in between breakfast and lunch, I can put them all after lunch, seemingly. So if that were the case, if there were not this restriction about something has to come between mealtime, then this is a pure stars and bars problem, in which any way I have of distributing stars in and amongst these 2 bars leads to a unique solution. And so this is a string of length 5 characters, and so there are 5 choose 3 ways, that's true, to form indistinguishable strings composed of 3 stars and 2 bars. So there are therefore 5 choose 3 ways to distribute the 3 activities into the 3 spots in the day, before breakfast, between breakfast and lunch, and after lunch. However, that's not the right solution to our problem, because in fact we can't leave this spot empty. So this particular star and bar based string that I've just written here would not be a valid solution to the problem. So I need to do some like subtraction or something. So let's now subtract, maybe this isn't a great solution, let's now subtract from all the numbers that we just counted. By the way, this is not a huge number, this is just 10. So let's subtract from all the ways we just counted, all the ways in which there are no stars in this middle slot. And okay, now just doing this in my head by talking it out, because the numbers are so small, well, given that there are only 3 stars, how many ways can there be no stars in between the 2 bars? Well, there could be 2 on the left. You could have 2 stars before breakfast and 1 star after. Vice versa, 1 star before and 2 stars after. Or 3 stars before breakfast and no stars after lunch. Or 3 stars after lunch and no stars before breakfast. So I count 4. Okay, so by just brute force counting, there are 4 strings in which there are no stars in between breakfast and lunch. So therefore, there are 10 minus 4 equals 6 ways to distribute the 6 stars. To distribute the 3 stars to the 3 spots. And of course, having now done that, there are just then 3 factorial ways to still order the non-meal activities with respect to each other. Okay, running out of space on this, I thought I probably would have to make another slide. There is a method number 4. Method number 4 attempts to less awkwardly count this this number of ways of distributing non-meal activities in and amongst the 2 meal activities. So how can we do this? Well, we can do this using a kind of even more sort of modified stars and bars kind of method. Now we build a tile, and this tile is going to look like B, and it has a blank on it. In other words, I kind of want to force there to be at least one activity after breakfast or before lunch, but let's just call it after breakfast because I think it's arbitrary. So if I want there to be at least one activity between breakfast and lunch, let me kind of like glue an activity spot, so to speak, to the breakfast marker. Okay, so now here's what I have. Whereas over here I kind of had this bar represented breakfast and this bar represented lunch. Now I have, this is again stars and bars if you really squint at it, but now the right bar is going to represent lunch and the left bar is going to represent breakfast plus an activity that comes immediately after breakfast. And therefore, the task of deciding how many non-meal activities come before breakfast, between breakfast and lunch, and after lunch, now I have full freedom. So now I don't have to do any of this subtraction anymore because now I just have, well, I have 2 stars. The stars represent activities, and I may distribute those 2 stars anywhere I want. There are 3 kind of free spots to distribute these 2 stars. I can distribute them before breakfast. I can distribute them to the between breakfast and lunch spot, which already automatically contains an activity because of the way I made my tile, and into the after lunch spot. And so, for example, here's one way to distribute the 2 stars. Put one before the first bar and one after. In other words, one before breakfast and one after lunch. But by building a blank, so to speak, into the by fusing a blank into the into the breakfast spot, I forced there to be at least one activity after breakfast. I think you get it. Okay, so how many ways are there to do this? Well, now this is just, again, a stars and bars problem. I have 2 bars and 2 stars. And so every unique, so this is star, bar, star, essentially, is the version of the picture I just drew. So, okay, clearly now we have a string of length 4 composed of 2 stars and 2 bars. And so there are just 4 choose 2 ways to distribute these to form indistinguishable strings from 2 stars and 2 bars. And, okay, what have I really done? Well, this particular combination, star, bar, bar, star, I now interpret as there's precisely going to be one non-meal activity before breakfast, then one non-meal activity after breakfast. That's the blank that comes glued to the B symbol, so to speak. Then there are no other stars in between these 2 bars. Therefore, I added no additional non-meal activities. And therefore, next comes lunch, and there's 1 star after the last bar. That last bar means lunch, so that means there's going to be 1 activity. So in other words, every string of length 4 composed of stars and bars represents a unique way of distributing 2 non-meal activities to the 3 non-meal activity slots. But I've already sort of taken care of the fact that there's guaranteed to be 1 in between. So I think this is quite kind of brilliant. And so anyway, that means that there are 4 choose 2 equals 6 ways of deciding how many non-meal activities take place in the various 3 spots, and then I still have to multiply by 3 factorial to consider the 3 factorial ways of permuting the 3 non-meal activities. Okay, so this method number 4, I think, is the true heir to method number 2. It is the principled solution to method number 2 that will work even if all these numbers were 5 times as big. I wouldn't have to go through these 6 tedious cases. Okay, so I think this is getting pretty intense here. Let's see. What do I want to do? I want to make a new slide, because I'm still continuing with this, because I got a couple more. Maybe this is anticlimactic now, because maybe we're kind of done. But there's even a method number 5. No, we're not done. What is method number 5? Method number 5 says, make sure I understand this correctly. Oh, method number 5 is a different kind of so-called complementary counting, where you count all the methods and then you subtract out the ones that are invalid. So let's see. Method number 5 says, all right, you know what? Let's just permute all 5 activities. Okay, so if I permute all 5 activities, then now, okay, so that could include, lunch and then breakfast immediately afterward. Well, that's certainly not allowed. Well, now, look, let's divide by 2, because in precisely half of these permutations, lunch will come before breakfast. And I only want to consider the ones in which breakfast comes before lunch. So let's divide by 2, and let's see how to explain this. By dividing by 2, I am essentially throwing out all the ones in which lunch comes before breakfast, because those are invalid. So that seems pretty convincing. Is that just totally blindingly obvious that in half of the permutations, lunch will come before breakfast? That's pretty obvious. I don't know what I would say if someone asked you to justify that further, though. Yeah. All right. Okay. I guess breakfast and lunch, there are an equal number of permutations in which breakfast comes before lunch. Well, I guess it's obvious, right? Because the first spot could be breakfast or it could be lunch, and those are equally likely. And then that's still true if neither were breakfast or lunch. Then when you get to the second spot, once again, there's an equal choice. So I guess that is kind of obvious. Okay. Anyway, what do I now have? I claim that 5 factorial over 2, that's counts all of the possible permutations in which breakfast comes before lunch. So that seems good. 5 factorial is 120, so that's 60. Now I need to take out all the ones in which... actually, this method is great. Now I need to take out all the ones that violate my other requirement. My other requirement says that there must be an activity that occurs between the meals. So, okay. So if I want to subtract... So what I now need to do is I need to subtract out all of the possible permutations in which breakfast and lunch come sequentially. Okay, well, this is a kind of now a separate problem that I've sort of already solved, so to speak. If breakfast and lunch come sequentially, then sort of glue breakfast and lunch together and think of the 4 activities as being, BL, mow the lawn, play piano, and read a book. If we had sort of insist now that breakfast and lunch are sequential, then really you can just think of breakfast and lunch as one sort of tile or something, as one event. And now I'm simply asking for the number of ways to permute these 4 events. And the answer is there are 4 factorial. Okay, this is great. There are just 4 factorial ways to permute the 4 things. The 4 things being mowing the lawn, playing the piano, reading a book, and breakfast immediately followed by lunch. Therefore, there are 4 factorial ways to do these 5 activities in which lunch immediately follows breakfast, And those are precisely the things that I needed to take out of my original calculation. So this is actually kind of just wonderful, I've decided. And so what do we get here? We get 5 factorial, which is 120 divided by 2. So that's 60 minus, and 4 factorial is 24. And so we also get kind of 36 in a sort of another way. All right. Woo! We are getting so smart now. Method number 6. This video is going to be 20 minutes long, and I'm still going to be on the first problem. Method number 6 says, this one might be sort of backtracking in elegance, but someone shared it, so here we go. Method number 6, kind of a follow-up on the tile thing, but now we build our tiles even differently. We build our tiles by, oh my gosh, how many activities occur between breakfast and lunch. So let's build a breakfast blank lunch tile. On the other hand, let's build a breakfast blank blank lunch tile, and let's do a breakfast blank 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 lunch tile. In other words, let's partition by, I guess this is in some ways just another example of partitioning by the number of activities that occur between breakfast and lunch. But somehow it's different or something. I don't know. Well. Now what? Give me 1 second to kind of process what's going on here. Why do I now multiply by 3 times 3 factorial? 3. Oh! I see. Okay, this is kind of cool. Okay, so now this is actually kind of different and maybe worth doing. Okay, getting this out of my brain from 13 months ago. Now this person, this was not my idea. Someone last year must have come up with this. They say, okay. So here are the 3 cases. This is totally great. This is totally worth doing. Case 1, case 2, and case 3. In case 1, there is precisely 1 activity between breakfast and lunch. Let's first fill in that activity. How many choices are there for which activity comes between breakfast and lunch? Well, there are 3 choices. And if there are 3 choices, now I've sort of kind of partially completed. I'm filling in the schedule of the day in a kind of a unique way. I'm saying there's going to be 1 activity between breakfast and lunch, precisely 1. Let's choose which activity it is. Having now decided that I'm going to do this particular single activity between breakfast and lunch, now I have 2 remaining activities. And where can those activities go? They can go either both before breakfast, or both after lunch, or 1 before breakfast and 1 before lunch. In other words, in any order with respect to this breakfast activity lunch combo that I've kind of penciled in. And so there are 3 ways to choose which activity comes between breakfast and lunch. And then subsequent to that, there are 3 factorial ways to permute the 3 remaining things. And the 3 remaining things are the 2 activities that I haven't yet scheduled, and this giant combo activity sort of consisting of, breakfast, activity, lunch. Okay, I think that makes sense. Let's do another one. Here, I have now decided that in case 2, that there are going to be precisely 2 activities between breakfast and lunch. Well, let's now fill in, let's decide, which activities there are that occur between breakfast and lunch. Well, there are 3 choices for which activity comes immediately after breakfast. Then, for each of those, there are 2 choices for which activity becomes immediately before lunch. And now, having decided sort of 3 times 2 ways to decide, to sort of plan out the block, the now block of 4 things that occur: breakfast, activity, lunch. I now have just 2 things to permute, and the 2 things to permute are this monster block activity and the one other activity, which can now go either before this monster activity or after. I guess that's kind of the yeah, let's do it that way. Okay, and then in case 3, well, I think you see now in case 3, I have 3 activities that occur between breakfast and lunch. So now there is only one sort of block. There's this block. It's just this big block, man. And there are 3 activities for which comes. There are 3 choices for which comes immediately after breakfast, followed by 2 choices for which activity becomes after that, and then 1. And so we get 3 times 2. And now there's just, I mean, if I want to be sort of analogous here, times 1 factorial, because there's only one sort of block. And so what do I get? I get 6 times, doing it this way, I get 6 times 3 factorial plus 2 factorial plus 1 factorial. And I guess this is kind of like a little bit like method 1, I guess. Yeah, it really is a lot like method 1. So that's 6 times what happened here? This is just garbage what I just said. Sorry. I guess I just do these all separately. I think there's no more deep thing to say, right? This is then just 6 times 3, so that's 18. This is 6 times 2, so that's 12, and this is just 6, and that adds up to 36. Okay, method number 7 is these are all great. These are just I can't imagine ever having not done this. Okay, method number 7 is brilliant now in even a new kind of way. Method number 7 says, okay, think of it like this. Let's, if it's the activities that have to occur in such a way that there's at least one activity between breakfast and lunch, instead of fixing breakfast and lunch and distributing the activities in between breakfast and lunch, that's annoying because I have to account now for this special case in which something has to go between breakfast and lunch. Let's instead, this is the only good way to do this actually in retrospect, let's instead block the activities. The only thing that makes that hard is that I don't know what the activities are. So let's call that activity number 1, activity number 2, and these are non-meal activities, and activity number 3. Let me just write just 2 here. So yeah, activity 1, activity 2, and activity 3, non-meal activity. Please interpret that as. Okay, well then let me distribute the meals in between those activities. And so by putting a blank here, this is just brilliant, right? And so much more simple because now breakfast and lunch can't occur sequentially because I am specifically inserting them into spots between activities. And if there happens to be no meal that occurs between 2 non-meal activities, then it just means they occur sequentially. And so actually this whole problem is just solved now, right? I have 2 things, breakfast and lunch, and I need to distribute them into these 4 spots. So this is now classic stars and bars, right? I have 2 stars, and let me think of these activities as being 3 bars. And these 3 bars are separating the the 3 bars are dividing up the 4 things, whereas the 4 things now are places for meals. And where could those meals go? Wait, no, I take it back. Sorry, it's not stars and bars at all. Never mind that. It's absolutely not stars and bars. It's just an even simple, more basic thing. You don't even have to have any background knowledge to do this problem. I just have 4 slots, and I just need to put breakfast and lunch into those 4 slots. So there are 4 choose 2 ways to choose which of the 4 possible time slots, those 4 time slots being before activity 1, between activity 1 and activity 2, between activity 2 and activity 3, and between activity after activity 3, there are 4 choose 2 ways to pick which 2 of them will be filled with a meal. And once I choose, say, those 2 spots, I shouldn't even use stars because that's maybe giving the impression that it's a stars and bars problem where it's not. I'm just putting sort of just pick 2, right? Of these, there are 4 choose 2 ways to do that, and 4 choose 2 is 6. And then, of course, the first one is breakfast. The other one is lunch, and that determines a unique ordering of meals and activities. But then, of course, I have to decide which activity goes in which place. Maybe it would have made sense to talk about that first, right? But like, order the 3 non-meal activities with respect to each other. 3 factorial ways to do that. And now sort of just now place the 2 meals into the 4 choose 2 spots that there are. Place the 2 meals into the 4 spots that there are between those activities. And there are 4 choose 2 ways to choose which spots the meals go. Okay, and so that is going to be 6 times 3 factorial, so that's 36. Okay, good. I'm gonna pause this video and come back and do the rest later. 1 problem down, 20 to go. Okay, we are back. The very next problem, number 3. Is it going to start getting any easier? Not really. This problem is actually just quite annoying. There are 4 kinds of coins in America. There are pennies, nickels, dimes, and quarters. How many ways can I make 29 cents? All right, well, here it seems that there should be some kind of like way to do this or something, but I don't think there is, or at least I can't come up with something. You can be kind of a little bit smooth about this by considering the cases in an organized fashion, like by whether or not we have quarters. Let's see, should I attempt to be cool about this? I didn't really plan this out in advance, but you're gonna either sort of like use a quarter or not. So maybe I'll call this like Q or something like that. And well, if you do choose to use a quarter, then you can have 1 quarter. But if we're trying to make 29 cents, there's only one way to finish that off. So that's 4 pennies. Okay, so that's one possibility. Then the other possibility is that there were not any quarters. So if there are not any quarters, then maybe the next question to ask is how many dimes are there? And well, so what am I going to do? I guess I'm going to label this 0 quarters or something like that. So if there are no quarters, then how many dimes can there be? Well, I guess 0, 1, or 2. Man, I really should have planned this in advance. But so I'll call this 0 dimes, 1 dime, and 2 dimes. All right, well, if there are going to be 2 dimes, then I think there are just 2 possible ways to finish that off, and that is with a nickel or with out a nickel. Yeah. So what are those 2 options? So within the 2 dimes category, this is just terrible. Please watch this on 3 times speed. Let me just go really fast. There's either gonna be no nickels or 1 nickel, and yeah. Well, okay. If there are 2 dimes and 1 nickel, then we're done. So I guess 2 dimes, 1 nickel is the other possibility. If there are no nickels, then we have to just finish that off with 9 pennies. So 9 pennies. Cha, 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 cha. So that's another option. Okay, what if there are no quarters and 1 dime? Then I gotta make up 19 cents, but really 15 cents because they're all gonna end with 4 pennies. Okay, so how do I make up 15 cents? I guess it's how many nickels I use now, right? So if I have 1 dime, then I'm gonna either use 1, 2, or 3 nickels. So This is the 3 nickels. This is the 2 nickels. And let this be the 1 nickel case. All right, well, if you have 1 dime and 3 nickels, that's already 25 cents. So there we go. 1 dime, 3 nickels, 4 pennies is one option. And 1 dime, I don't feel like writing this over and over again. So let's just follow the chart, everyone. 0 quarters, 1 dime, 2 nickels. And therefore, we would have to finish it off with 5, with 1 nickel and 5 pennies. What am I doing? Is that right? 1 dime, 2 nickels, that's 20 cents. So yeah, 1 dime, 2 nickels is 20 cents. Wait, I can't have 2 nickels? No, what am I talking about? Oh my god. 1 dime, 2 nickels is 20 cents. So then the final would be plus 9 pennies. Okay, so this is 1 dime, 2 nickels, 9 pennies. I guess I should just keep writing this every time. Okay, and what if there's going to be just 1 nickel? Then what are we talking about? We're talking about no quarters, 1 dime, 1 nickel. Well, that's only 15 cents, so there must be then 14 pennies. So that is the other option. Geez, this is terrible. Okay, if there are no dimes, then I guess there are like 5 options for nickels, right? There could be anywhere between 1, so, oh man. So there's no nickels, 1 nickel, it's not even good handwriting, 2 nickels, 3, 4, and 5 nickels. So 3 nickels, 4 nickels, and 5 nickels. But I guess at this point, then we're just done. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. What am I missing? No nickels, 1 nickel, 2 nickels, 3 nickels, 4 nickels, 5 nickels. I must have missed one. This is just embarrassing. So wait, if there's either a quarter or not. If there's a quarter, there are 4 pennies. If there are no quarters, then how many dimes are there? Oh, there could have been no dimes. I can't. 0 dimes, 1 dime, or 2 dimes. If there are 2 dimes, then that's 20 cents. So we need to make up 9 cents. 0 nickels or 1 nickel. There are no quarters. This is even just making total sense. Why does my paper says 13, but I think I'm only going to end up with 12 somehow. 1, 2, 3. 4, 5, 6, 7, 8, 9, 10, 11, 12. I don't know. I don't know what happened, but I'm already disgusted with my own work here. 2 dimes. It's a quarter or there isn't. It's a quarter or there isn't. There are, yeah. I don't know, man. Could there be, if there are no quarters, there are... If there are no dimes, I must have missed one somehow, but it's too embarrassing for me to slow down enough to finish it off. Okay, let's see what happens if there are 5. If we choose 5 nickels, then of course that is just 5 nickels. That's 25 cents and 4 pennies. If there are 4 nickels, then that must be 4 nickels. That's 20 cents and 9 pennies. Because this is all within the no dimes case. If there are 3 nickels, then we're talking about, well, 3 nickels and 14 pennies. If there are 2 nickels, then we're talking about 2 nickels and 19 pennies. If there's 1 nickel, then we're talking about 1 nickel and 24 pennies. And if there are no nickels and no dimes and no quarters, then we're talking about 29 pennies. So why do I say that there are... It's embarrassing to spend more time on it, but it's like more embarrassing to not have the freaking answer. 2 dimes, 9 pennies. Sure. 1 dime, 2 nickels, 9 pennies. 1 dime, 2 nickels. Oh, there we go. Because I'm just really, really that dumb. Which is, I forgot the possibility that there would just be no nickels. So yeah, okay, I figured that's what had happened. Some branch in the tree was just neglected, duh. So yeah, if there are no quarters and 1 dime, then there's going to be 1 dime and 19 pennies. 19 pennies. and here is a penny, and here is the thing. Okay, so there is some logic to, had I practiced this in advance, I could have made a more beautiful tree. There's some logic to what's going on here, which is, this is kind of discrete math, I guess. You partition the set of possibilities by the number of quarters, and then within the quarter decision, you partition by the number of dimes, by the number of nickels and stuff. So what makes this problem interesting? What makes this problem interesting is that it's an annoying problem for which there is no good solution. So sometimes some problems don't have elegant solutions. Sometimes just like raw brute force casework is required. And so you should, just to keep yourself honest, every now and then you should try to, and in fact successfully, solve a problem just by raw brute force casework, just so that you are aware that, sometimes that's just the way and there is no other way. At least I don't think. From 10 years of going over this problem live in class with smart people, no one ever came up with anything better than this. Just could have been a prettier chart and maybe done in half the time. All right, so that's the number of ways. The answer to this problem is there are 13 ways to form 29 cents. Okay, there are probably still some sort of principles going on here, but not really. How many distinguishable ways can I have 3 of these coins? Well, if you care about like money and stuff, then if you're given a choice, hey, I have a whole giant pile of pennies, nickels, dimes, and quarters. Take any 3 that you want. Well, if all you care about is money, then you just probably take 3 quarters. But if you've ever played this game with little children, they don't know how much things are worth. In fact, they have no concept of money at all. And they will just as likely choose pennies, for example, because they're, shiny or something. So, all right, how many ways can I do this? Well, this is now just a classic stars and bars problem, right? We have pennies, nickels, dimes, and quarters. In other words, 4 categories of coin. And we can think of those 4 categories of coin as being divided up by 3 vertical bars, so producing 4 regions. And now, if I am going to obtain 3 of these coins, then I can do that by placing my 3 stars in and amongst these 3 bars in any kind of way that I choose in each each string of length 6 consisting of 3 bars and 3 stars will be a different way of having 3 of these coins. And so the answer to this is 6 choose 3, which is, I guess that's like 20. 6 times 3, yeah, that's 20. So, better not get that wrong. That would be embarrassing. Yeah, no, it is 20. So there are 20 ways to do this. Gossett says, list them all out. No, man, I've already done your tedious problem. I don't want to do even more tedium. Okay, good. Here comes a couple more fast ones now, or at least I think they're fast. Number 4, in how many ways can 5 tomato plants, 2 rhubarb plants, and 7 raspberry bushes? I swear he does this on purpose. Tomato, rhubarb starts with an R, but so does raspberries. Just cruel. So let's just call this B for barb. That's what the cool kids are calling rhubarb nowadays, barb. So I got 5 tomato plants. I got 5 of these, and I got 2 barbs, and I have 7 raspberries. And how many ways can I arrange these plants along a garden strip if there does not need to be any distinction among the plants' bushes of the same type? In other words, just how many ways? This is just the classic multinomial theorem counting principle at work here. The tomato tomato plants are all indistinguishable from each other. The barbs are indistinguishable, and the raspberries are indistinguishable. So the question is equivalent to, if I have a string consisting of 5 T's, 2 B's, and 7 R's, 5, 6, 7. How many strings are there? How many distinguishable strings are there consisting of 5 T's, 2 B's, and 7 R's? And the answer is, there are many ways to think about this, but as I talked about in the previous video from 2 weeks ago, one way of doing this, the sort of fast way, is to say, okay, and this is even what we did in pre-calc, this is a string of length 17, so there are 17 factorial ways to permute the characters of this string, but then of course that vastly overcounts because the t's in the string are all indistinguishable from each other, and so you should divide by 5 factorial because there are 5 factorial ways for the t's to all swap places, and 2 factorial, and you also divide by 7 factorial. So that is the answer to the problem. If you want a little bit more of a deep explanation, then you can say something like this. Well, this is also known as, there's a sort of a symbol for it, I guess. 17, 527 is 17 multinomial 527 is a way you can pronounce that. So what is 17 multinomial 527? It's by definition the number of ways given 5 objects of one type, 2 objects of another type, and 7 objects of another type, of ordering them, of ordering them, I guess. So good, so I've argued loosely that this is the correct formula for this. But a more clear proof, this is just a complete repeat of the previous video, but I'll just do it really fast. A sort of more, I think, coherent proof of this fact is, okay, take this symbol, which by definition is the number of ways of producing strings of length 17, consisting of 5 of one letter, 2 of another letter, and 7 of another letter, indistinguishable strings. And now distinguish them in some way. And so, in other words, get really, really close to those 5 tomato plants and notice that they actually are not just the exact same tomato plant, but they're a little bit different. And so, having decided the positions of the tomato plants, the barb plants, and the raspberry plants, there are then 5 factorial ways for you to permute the 5 tomato plants. And then, so for every way there is of deciding which of the 17 spots are going to be filled with tomato plants, barb plants, and raspberry plants, there are 5 factorial ways to permute the 5 tomato plants amongst themselves. And for each of those ways, there are 2 factorial, or just 2, ways to swap the places of the 2 rhubarb plants. And then for every one of those ways, there are 7 factorial ways to permute the 7 raspberry plants amongst themselves. And having now done it in this order, I have now, in fact, counted every possible permutation. And so this is now just a kind of a mini little combinatorial proof, right? On the one hand, there are 17 factorial ways to permute the 17 plants. On the other hand, we could count the same thing by first choosing which type of plant goes in which spot, and then permuting them within those spots. Okay, so this to me is like a proof of this formula, and it's really no different than the proof I gave earlier, but I think it's clear because instead of division and talking about overcounting, you're just going to solve it as like as a pure combinatorial identity. Okay, good. Faster, more. Number 5. James and a friend played 14 games of tic-tac-toe one night. In how many ways can James end the night with 8 wins, 2 ties, and 4 losses? That's pretty embarrassing because you should tie tic-tac-toe every time. So, okay, if this is the final count of the night, basically, that James won 8, tied 2, and lost 4, how many possible ways could this all have gone down? Well, that's just equivalent to how many strings are there of length 14, consisting of 8 W's, 2 T's, and 4 L's. And that's the exact same thing, that's just exactly what we've been talking about. It's 14 multinomial 8, 2, 4, which is 14 factorial divided by 8 factorial, 2 factorial, 4 factorial. So this is classic multinomial counting. Okay, number 6. In how many ways can you choose 4 countries to visit in 4 consecutive months? Okay, this is a controversial problem. And I lost my spot in my... Sorry about this. Oh, man. So I need to go back to this day, February 28th, 2020. Okay, I think I got it now. That wasn't too bad. Yikes. 1 second, 1 second. 1 second. Yeah, okay, so I have this kind of chart that I made last year. All right, so this is an interesting problem because, because it's ambiguous. And since it's ambiguous, then we can solve it in different ways. In how many ways can you choose 4 countries to visit in 4 consecutive months from a list of 9 possible countries, including France and Germany? If France, okay, so let's just do it, right? France, Germany, I got 9 total countries. So I don't know, what are those countries? Japan, Canada is always nice. Brazil, maybe we want to go to Russia. That sounds wonderful. What do I have left? 3 more. Maybe Egypt would be nice. 2 more. Indonesia and Lebanon. Okay, there we go. All right, so France, Germany, Japan, Canada, Brazil. I already forgot what R was. Russia, Egypt, Indonesia, and Lebanon. All right, well. Great. Now there are 4 months coming up. Let's just call them January, February, March, and April. And here's what's going on. I need to schedule like a trip. And cha. In how many ways can you choose 4 countries to visit in 4 consecutive months from a list of 9 possible countries, including France and Germany? Okay, and now he's going to sort of start to ask, well, France must be visited. So perhaps you have a sick grandmother in France, and so like you got to go visit your grandmother in France. So you got to go to France. What if you need to go to France or Germany, but not both? Okay, so So yeah, you're gonna go to sure. Okay, yeah, you're gonna go to France or Germany. You have good friends in France and Germany, but if you go to France, your German friends will come visit you in France. If you go to Germany, vice versa, something like that. You don't want to waste going to Europe twice. That would be lame or something like that. I don't know. And then France and Germany must be visited, but neither country can be visited during the first of the consecutive months. So basically, don't go to France and Germany during January. All right. I claim that this is a confusing problem because at the very beginning, we have to decide whether we should interpret Gossett as saying that we can go to the same country twice or not. So if you're gonna go now, if you just have your guidebook and you just want to go to different countries, because you're only gonna go on a finite number of vacations in your life and you want to see the world or whatever, then maybe you think it's obvious that we would choose to go to 4 different countries in the 4 different months. But maybe you just have somewhere that you just love and you just kind of go back again. I think it's perfectly reasonable to go to Italy and then just go back to Italy again 2 years later and just keep on going back. I would love to go back to some of the places I've been already, even in consecutive months. And so maybe you just have, as I mentioned last year in class, maybe you just have like a secret boyfriend or something who lives in Brazil, and you're just gonna go visit him every single month, say. Okay, we need to decide. We need to answer. I claim that this is really 6 problems based on the ambiguity built into the problem. You might think this problem is actually not ambiguous, and that that the same country is possible because hey, Gossett didn't say it wasn't. But my experience with student psychology is that in fact you take as your default that you would go to all different countries because why not? Okay, so I'm going to hereby answer this problem now in 6 different ways. I'm going to answer the 3 parts of the problem, but based on these 2 different interpretations. Okay, let's go. I can't decide what the order. Let's start over here. Suppose because I think this is actually maybe this whole column is kind of just easier or something. Okay, so what if you're going to visit all different countries? Okay, well, France must be visited. Well, okay, look, man, then you're going to either visit France in January, February, March, or April. So I have 4 choices for when to visit France. And subsequently, now, once I decide in which month I'm going to visit France, then I'm just going to fill in the 3 remaining months with 3 more countries. So personally, I like to think of myself as choosing the countries first. So yeah, there are 8 choose 3 ways of picking which 3 non-France countries to visit from the remaining 8 countries. Having chosen which 3 countries to visit, I then have 3 factorial ways to decide the order in which to visit them. Okay, of course, 8 choose 3 times 3 factorial is just 8 permute 3, but no one, my experience is that no one really uses that silly HP3 notation after a while. You just think of it as there's just no need for it, right? 8 choose 3 is just the number of ways, so just think of it as 2 separate things. First choose your 3, then permute them. To me, that seems more intuitive. So let's not have all this notation for things we don't for concepts we don't need. Okay, so there we go. Let's go a little faster now. What about part B? France or Germany must be visited, but not both. Okay, well, let's just choose which it is, whether it's France or Germany. And great. Now I've decided which one it is. Now let me pick my 3 remaining countries. Oops. So there are now only 7 countries to choose from. So there are 7 choose 3 ways to pick which 3 countries from the sort of non-European ones, from the non-France, non-Germany. Now I have my 4 countries. Now there are 4 factorial ways to permute those 4 countries. In other words, to decide what order to do them in. I guess I could have also done the previous problem that way. Of course, it's the same thing, but maybe this was needlessly complicated. After all, I really just choose my 3 countries, which is 8 choose 3, that are not France, and then permute them. In other words, there is a kind of 1% different way of solving this one, which is perhaps a little bit more elegant, which is 8 choose 3 is the number of ways of picking which 3 countries to visit that are not France, and then now that I've decided that I'm visiting France and the following 3 countries, then it's just 4 factorial ways to permute those 4 countries. Of course, that's the same thing. So, all right, feeling good. Okay, now what? I see that I've run out of room a little bit or something here, because this one is maybe the most complicated. If France and Germany must be visited, but neither country can be visited during the first of the consecutive months, then, first of all, I guess I should choose. So here's one way of doing it. I'm looking at my own thing. It's kind of confusing. Okay, first, let's choose. This is one way of doing it. First, if I have to visit France and Germany, but I can't visit them during January, then let's decide which of the 3 remaining months are going to be filled with visits to France and Germany. So there are 3 choose 2 ways to pick of the 3 months, February, March, and April, which 2 will be filled with trips to France and Germany. Having decided which 2 will be filled with trips to France and Germany, there are then 2 ways to decide whether I do it Germany-France or France-Germany. Okay, so now I've partially filled in my calendar with, I've filled in my calendar with the trips to France and Germany. Now I just need to do the rest, which is to say there are 7 choose 2 ways to pick which of the 2 other countries I'm going to visit that are not France or Germany. Right, because I only have 2, I'm only visiting 2 more countries now, so 7 choose 2. And now, once I pick those 2 countries to visit, I multiply by 2 again to give me the order in which I visit them. So that's certainly the right answer. Is there a slightly more elegant way to do this? I don't know about more elegant. Maybe it's like more simple or something. Let's see if I understand this. Okay. So yeah, how many countries are there? How many choices are there of which countries to visit in the first month? Well, in the first month, you can visit any country you want, except for France and Germany. So I have 7 choices for which country to visit in the first month. How many choices do I have for which countries to visit in the... No. Then, having chosen which country to visit in the first month, now there's only one more country left to pick. So now there are 6 ways to pick what other country I'm going to visit besides France and Germany and the country that I visited in January. So first, the 7 is which country I visit in January. For every way of choosing which country to visit in January, 7 choices. It just can't be France and it can't be Germany. There are then 6 choices for what is going to be my other country to visit. And now that I've decided that I'm going to visit, say, Indonesia, well, now I just have to decide on the order between Indonesia, France, and Germany. And there are 3 factorial ways to do that. So that's an alternative way of doing this problem. Okay, now let's go to the, which I think is harder, same country possible. Okay, so I have to visit France, but now I'm including possibilities in which I say visit France, Canada, for example. Or maybe even just France, or France, Brazil, France, or something like that. So now almost everything is on the table. The only rule is I gotta visit France at least once. And so now I think the natural way to do this is with so-called complementary counting. 9 to the 4th represents the total number of possibilities if there are absolutely no restrictions. So in each of the 4 months, I can visit any one of the 9 countries. Okay, so I have 9 choices for the first month, 9 choices for the second month, 9 choices for March, and 9 choices for April. So there are 9 to the 4th ways. Okay, but that is going to include schedules, plans in which I don't visit France. But built into part A is that France must be visited. So let me subtract out all the ways in which I don't visit France. Well, now if I don't visit France, then it just means that in every single month I didn't choose France. And so there are 8 to the 4th ways to not visit France. It just means that in each of the 4 months you had 8 choices, 8 because not going to France. So 9 to the 4th minus 8 to the 4th is the number of ways to make this schedule, assuming that you do visit France, but considering the possibility now that we have maybe repeat visits to countries. Okay, now what? France or Germany must be visited, but not both. Okay. France or Germany must be visited, but not both. Do I understand this? My own work. I think I do. Okay, so first of all, let's decide which it is. France or Germany. Okay, so there are 2 choices, whether we visit France or Germany. If we visit France, we don't visit Germany. If we visit Germany, we don't visit France. So once I have chosen to visit, say, France, then the rest of the problem now is just like the first problem. Note that I'm not talking about visiting France in the first month. I'm talking about visiting France at all. So I'm interpreting now, this gets kind of hard. France or Germany must be visited, but not both. So I'm interpreting this as I'm counting now the number of ways to visit France at least once and Germany not at all. And I'm counting the number of ways of visiting Germany at least once and France not at all. Okay, so if I choose it to be France that I'm visiting, then well, if you're visiting France, then what? Then you now are free to do whatever you want, except you just can't go to Germany. So once again, there are 8 to the 4th possibilities, total possibilities, because now Germany is just impossible. So I have 8 choices each month. I have 8 choices, but that includes the possibilities in which I every time chose not to go to France. But I need to go to France, so I need to subtract out 7 to the 4th, because 7 to the 4th is all of the ways in which I didn't go to France. So this counts all the possible ways of going to anywhere but Germany, minus all the ways in which I don't go to France either. Then 8 to the 4th minus 7 to the 4th is all the ways of going to France at least once, but not going to Germany at all. And I multiply by 2 because now I repeat that for the other combination. Okay, I think this is making sense. This is taking too long. Part C. Now, France and Germany must be visited, but neither country can be visited during the first of the consecutive months. All right. Well, I'm going to split this up into casework. So, France and Germany must be visited, but neither country must be visited during the first of the consecutive months. 2 France, 1 France, 1 Germany, 1. I just straight up don't even get this. Oh, okay. All right, so I have to go to at least France and Germany. Okay. So now the question is, if you have to go to at least France and Germany, what are you going to do with your other 2 months? Okay, one thing you could do with your other 2 months is take 2 trips to France. Okay, so you could just choose to fill in the rest of your calendar with 2 Frances. Or you could choose to fill in your calendar with 2 Germanys. Or you could fill in your calendar with 2... Wait, this doesn't make any sense. 1 France, 1 Germany, 2... I don't even understand what I've written here, and I'm not really thinking so clearly right now. Let me just start with the counting, and then I'll explain the interpretation of what they mean later. There's 7 choices for what? What? France never must be, but neither country can be. Oh, I see. Okay, watch this. I have to go to France. I have to go to Germany, but I can't visit either country during the first of the consecutive months. Therefore, since I can't visit either country during the first of the consecutive months, it means I must be going to at least one non-France, non-Germany country. Okay, so therefore, every one of these trips is going to look like this. There's going to be 1 France, at least. So at least 1 France, greater than or equal to 1 France. There's going to be greater than or equal to 1 Germany. And then there's going to be greater than or equal to 1 other. Okay, so I guess the 2 possibilities are that I, with my 4th spot, I can either revisit France, revisit Germany, or go to a 4th country. Okay, let me try to explain that one more time. I have 4 countries I'm going to visit in some kind of order. I have to go to France once. I have to go to Germany once, and I have to go somewhere in January. So, therefore, that's automatically 3 different countries are going to get visited. And now, with my 4th remaining option, I can either revisit France, revisit Germany, or go to a new country. So that's my partition. So revisit France, or revisit Germany, or new country. In other words, a 4th country. Okay, well, if I'm going to revisit France, then that means that my 4 countries that I'm visiting are France, Germany, and a 4th one. Okay, so here we go. Now I'm ready to count them. I have 7 choices as to what country to visit in January. Then I have to simply order my France, Germany visit. Well, there are 3 choices for where Germany goes. Germany's going to go in either February, March, or April. And then the other 2 will be France. Done. Plus, now it's the same kind of thing. Now if I'm revisiting Germany with my 4th free spot, then I'm going to go somewhere in January. 7 choices for which non-France, non-Germany country to visit in January. Now, my 3 remaining months, February, March, and April, are going to be filled with 2 trips to Germany and a trip to France. So there are 3 choices about which month is going to be the trip to France. And then the other 2 will be Germany. Plus, now I have 7 choices for which country to visit in January. Then I have 7 choices for what my 4th distinct country is going to be that I visit at all. And now I simply have to decide between February, March, and April the order between France, Germany, and my 4th country. So there are 3 factorial ways to permute France, Germany, and the 4th country that was chosen here. Whew, that was so hard. Oh my god. Okay, good. Putting this phone away. I have no more notes. Well, I did do this, but I did this like a long time ago, like 10 years ago or something when I was dumb. So I'm not 100% sure these are all right. But I think there's a couple of easy ones now coming up. Number 9, a piano has 88 keys, 52 are white, 36 are black. In a standard octave, there are 7 white and 5 black keys. How many chords consisting of 3 white and 2 black keys are there in a standard octave? Okay, so this is almost like an easy problem because assuming that you have no musical principles are at play. Fortunately, I don't know any music principles, so I'm not going to be distracted by that. I just have 7 white keys and 5 black keys. This whole 88, 52, 36 thing was a complete misdirect that has nothing to do with the problem. Basically, an octave contains 7 white keys and 5 black keys. How many chords consisting of 3 white keys and 2 black keys are there in a standard octave? Well, from amongst the 7 white keys, there are, by definition, 7 choose 3 ways of picking 3 of those keys. And for every way there is to pick which 3 white keys you are going to play, there are 5 choose 2 ways to pick which 2 black keys you will play from amongst the 5 black keys, and so you multiply them to get the total answer. Woo! Good. Number 10. Oh, this is also a great problem. A local pizza store offers a choice of 7 toppings and 3 sizes, small, medium, and large. How many distinct pizzas do they offer if you may use any number of toppings, but toppings cannot be repeated? Okay. So, toppings cannot be repeated. That means you can't ask for like a double order of mushrooms. You just have 7 toppings, and you just need to decide, which 7 toppings is it going to be? But seemingly, you can just ask for any number of toppings. So you can just be like, this is like maybe, if we were doing this live, I bet someone would do this problem maybe like the bad way. The bad way is to partition by how many toppings you want. And then to kind of pick which toppings or something like that. So, you may use any number of toppings, maybe suggests that somehow the number of toppings is relevant or something. So, okay, let's go. If I have 7 toppings, there are 7 choose 0 ways of picking which toppings I want. And, that's just one, right? There's just only one way to do that. 7 choose 0 is 1. But there are certainly 7 choose 0, which is 1, ways of picking no toppings, if you just want no toppings on your pizza. Okay, how about if you want to have 1 topping? Well, there are 7 choose 1 ways to pick 1 topping. Because there are 7 toppings and you're picking 1. Okay, what if you decide, so here I'm counting the number of 0 topping pizzas. Here I'm counting the number of 1 topping pizzas. Now let me count the number of 2 topping pizzas. 7 choose 2. Sorry, I got a little bit distracted, but I'm back on track now. This is really quite easy, right? You have your 7 toppings. No, this is a bad way of putting it. La 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 la. This is an easy problem, but I'm just zoning out. 7 choose 2 is the number of ways of picking which two. 7, if you're deciding that we're counting now the number of 2 topping pizzas. If you decide that you're going to have 2 toppings, then you have 7 choose 2 ways of picking which 2 toppings they are. That's all there is. Okay, and then suppose you count the number of 3 topping pizzas. There are 7 choose 3 ways of choosing which 3 toppings, and then 7 choose 4, and then 7 choose 5, and 7 choose 6 is the number of ways of choosing 6 toppings, and then 7 choose 7 is the number of ways of choosing all the toppings. Okay, but of course, and maybe you were already, frustrated with this because this is not the good way to do this problem. I think live last year in 2020, Stein wandered into the room and he solved the problem this way. This is like kind of the bad way to do it. Not bad, but not efficient. This does count all the number of possible pizzas, partitioned by how many toppings you are going to have on your pizza. If that was maybe something that was relevant to you, because perhaps it was a different price based on how many toppings you have, and you want to kind of factor that in or whatever. But of course, there's a simple answer to this. If you want to know how many possible pizzas are there, instead of partitioning by topping, just go through every topping and decide, do I include that topping or not? Pepperoni, yes or no, 2 choices. Mushrooms, yes or no, 2 choices. Green peppers, onions, pineapple if you're some kind of weirdo, or whatever. So for each of the 7 toppings, there are 2 choices. Therefore, this is 2 to the 7th. Okay, so this was meant to be in a normal year, not Zoom school, not pandemic. We would have gone over this. We would have spent a whole block basically going over this homework assignment, and this video is going to be longer than 90 minutes. I can promise you that. And that this block would happen, just before the introduction to combinatorial proofs, and this is kind of like an introduction to combinatorial proofs. You sort of discover combinatorial proofs naturally while solving counting problems, especially if 2 people solve the same counting problem in 2 different ways. Well, then you've stumbled upon a proof, basically, of some combinatorial identity, and this is one we've already seen. Oh, okay, what's the answer to this problem? Then the efficient way to do this problem is just to say, I have 3 choices for what size, and then there are 2 to the 7th ways of choosing for every topping whether to put it on or not. So that's just the answer to the problem. Okay, are there a couple more easy ones coming up? I hope so. 11, determine the number of words, not necessarily words, found in the English dictionary. Come on, Gossett. We have a term for that. We call them strings. Just call them strings, man. That can be formed using each of the distinct letters in the word lollipop. Okay, well, this is pretty easy. Lollipop. This is the kind of problem that we would have solved back in Pre-Calc C even, but now maybe we'll be doing it with more understanding. This is 4, 5, 6, 7, 8. This is 8 characters, but there are way fewer than 8 factorial possible strings. Because built into the notion of a string is that the each character is either O, I, L, or P or whatever. So the L's are all indistinguishable from each other. The P's are indistinguishable. The O's are indistinguishable. So we need to divide by 3 factorial, 2 factorial, 2 factorial. Let's see, did I do that correctly? 5, 6, 7, and then there's 1 I. Yep. So that's just the answer. If you want to be even more kind of smooth or something, you can call this just a straight multinomial problem. So you can just answer this problem with 8, 3, 2, 2, and I suppose we should say 1 now. 8, 3, 2, 2, 1. Okay, good. Number 12. Although repeatedly warned not to play with food at the table, Karen spends time organizing her M&Ms. How many ways can she arrange 5 red, 3 green, 1 blue, and 3 brown? Once again, M&Ms in a line on the table. This is just straight multinomial. Answer to this problem is 8, 9, 10, 11, 12. It's just 12, 5, 3, 3, 1. Or 12 factorial over 5 factorial, 3 factorial, 3 factorial, 1 factorial. You can write that if you really want to. Okay, that's all I have to say about that. All right, this freaking problem. Okay, let's go. This required me to read this sort of multiple times very carefully. So, all right, consider the set A, B, C, D. All right, so let me think of these as 4 people. A, B, C, and D. They're all different people. Okay. what are we doing? Use the multinomial counting theorem to count the number of ways there are to partition S into subsets of size 1, 1, and 2, where the subsets are labeled X, Y, and Z respectively, then list all the partitions. Okay, so we want to divide these 4 people up into groups of size 1, 1, and 2. But kind of like, okay. In some ways, let me see how I want to answer this question. Yeah, in some ways, B is the more natural thing, right? It's like here you have these 4 people, and you need to split them up into groups of size 1, 1, and 2. But part B says how many ways are there to partition them into unlabeled subsets. Well, if you're partitioning them into unlabeled subsets, then you're really just asking how many ways are there to divide 4 people up into 3 groups of size 1, 1, and 2. Well, that's kind of easy, right? Because 2 of them are going to be paired and the other 2 are not. And so the way to do this is just 4 choose 2, because there are 4 choose 2 ways of picking which 2 of your 4 people are going to be paired. And once you choose the 2 that are paired, then the other 2 are going to be alone. So that's kind of like, the only thing that makes this hard is just this strange choice of unlabeled subsets. So you can think of dividing up the 4 people into groups as dividing up into them into unlabeled subsets. But suddenly, if the subsets are labeled, well, then we might as well just be saying, okay, look, there's X, there's Y, and there's Z, and, this is going to be of size 1. So one person's going to go here, one person's going to go here, and 2 people are going to go here. Okay, well, this is a similarly easy problem because now I just need to think of this as 3 rooms. This room contains enough space for 1 person, this room contains enough space for 1 person, but this is a double room. So how many ways are there to put the 4 people in these 3 rooms? Well, that's just easy, right? 4 choices for who goes in room X, and then 3 choices for who goes in room Y, and then you're just done? I think you're just then done. Why do I have so few? So I guess the answer is just 12. I guess the answer is just 12. I now have some conflicting information written on my piece of paper, so now I'm like doubting myself, but surely it's 12, right? That's because there really are 4 choices for who goes in room X. And then there are 3 choices for who goes in room Y. So then there are 2 choices for who goes in room Z. Alternatively, yeah, this is just right? Because alternatively, you could think of it as, let's see which 2 of them are going to be paired. Well, there are 4 choose 2 ways to do that, which is 6. But then, after having decided which 2 go in room Z, there are then 2 choices for who goes in room X and who goes in room Y. So the answer is definitely 12. Gossett says list them all. I mean, this is a good thing to do for beginners or something like that. Sometimes when the numbers are small or even medium, if you just tediously list it all out, then you can confirm that you're right. If you wanna know the real answer to this, deep down, this seems kind of cruel, right? Okay, so if we're gonna do this, what is it? Well, who can go in room X? A could go in there. If A goes in X, then B could go in Y, and then C and D are going to go in there. But of course, if A goes in, then potentially C could go in instead. And if A goes in, then D could go in. And then I guess there's just going to be, right, B, A, B, C, B, D, C, A. So these are going to be the 12 answers to this problem are going to all look like this: D, A, D, B, and D, C. And then if A and B go in room X and Y, then C, D, and then B, D. I guess this isn't too bad, to be totally honest. I was doing a lot of whining. This is C, D. This is A, D. This is A, C. This is B, D. This is A, D. Embrace the tedium. A, B, B, C, A, C, and A, B. Okay, so actually that only took like a minute. There is something to be said for like forcing yourself to write out every single partition. Somehow your brain, like deep down, like in some kind of reptile corner of your brain, like when you just do something repetitively over and over and over again, and it's very, very time consuming and very, very annoying, some kind of neuron fires that's like, I wish I were smart and there was some fast way to do this. And so somehow, like, you can actually, like, learn to be better at counting problems by, like, torturing yourself with listing out every single tedious case, and somewhere your brain says, we better learn how to do this more efficiently so I can avoid this kind of time-consuming stuff in the future. All right, that's my, like, weird, totally unsupported garbage psychology that I just invented. 16 is, I believe, the exact same problem, but now maybe more complicated or something. Let's go. Did I use the multinomial counting theorem? Like, I just straight up didn't, right? Oh, I guess, if you want to use the multinomial counting theorem, then the way you would do it is you would say, let A, B, C, and D be sort of like standing here in a row or whatever, and now I have one copy of X, one copy of Y, and 2 copies of Z, and I'm sort of distributing them around. So every, like, X, W, not W, what am I talking about, W? X, Z, Y, Z is like a string, right? And X, Z, Y, Z is a string consisting of 1 X, 1 Y, and 2 Z's. And that is a way of assigning to the 4 people the name of the room that they're supposed to be going to, using the labels. So if I really want to do what Gossett says and use the multinomial counting theorem, an alternative way to do part A of this problem is to think of it as how many strings are there of length 4 consisting of 1x, 1y, and 2 z's. The answer to that is going to be 4 factorial over 2 factorial, 1 factorial, 1 factorial. So that's just another way to do it. Of course, that just is, right, I hope? 12, yeah. Good. Okay, so now this is a repeat of the same problem. Let's see if you get it. Now things are more complicated because I have 5 people. Use the multinomial counting theorem to count the number of subset ways of participation. So now I have W, X, Y, and Z. This room is of size 1, 1, 1, 2. Well, again, I don't think I need the multinomial counting theorem for this because, like, come on, right? There are now 5 choose 2, which is 10 ways to decide who gets paired in room Z, and then I just and then there are 3 people left over, and there are 3 factorial ways to permute them. So the answer to this is 10 times 6. This is just 60. Alternatively, you could do it even more simply as just, dude, there are 5 choices for who goes into room W, then 4 choices for each of those. There are 4 choices for who goes into room X. Then for each of those, there are 3 choices for who goes into room Y, and then the rest is just determined. So the other answer is that this is just like 5p3 or whatever. So that's also 60. Or we could use the multinomial counting theorem, which says that you are passing out 1 W, so you're considering all the strings of length 5 consisting of a W, an X, a Y, and 2 Z's. And so that's going to be 5 factorial over 2 factorial, 1. I'm getting tired of writing 1 factorial, so I guess I'll just stop. So 5 factorial over 2 factorial, which is also 60. Okay, good. And now if they're unlabeled, now, is this, once again, an easier problem? I guess it is, because if they're unlabeled partitions, then the only thing to decide is, again, who's being paired. So there are 5 choose 2 ways to pick which 2 will be in the set of size 2. I guess that's the way to do this problem. And that's just 10. Okay, I was going to take a break because I was getting kind of tired and hungry, but maybe I'll just push on and just finish this crap off. This is the hardest problem maybe in the whole homework. And there are years where I've spent 20 minutes, half an hour more even talking about this. This is so hard. What makes this problem hard is it's so tempting to do things that are in fact wrong. Okay, and I love what Gossett has done here. He's really set the tone for the class by giving these extremely tedious, long stories, which get you in the frame of mind of really thinking about what's going on. So, suppose that 7 students in Mrs. Corner's 5th grade class and 3 chaperones are going on a field trip to the swimming pool in 3 vans that hold 2, 3, and 4 passengers respectively. How many possible ways are there to transport the 7 students to the swimming pool using all of the vans? Assume that the 3 chaperones are the drivers of the vans, but that it is not a concern in this problem which chaperone drives which van. How should you account for the empty seats? Okay, so this is a great problem because even this little parenthetical comment that he makes right here, using all of the vans is not even necessary, because you might at first think, okay, so let's draw a picture. What is the picture? There's 7 kids. We got 3 vans. What do the vans look like? Well, there's a driver, which is a chaperone, and then the vans hold 2, 3, and 4 passengers respectively. Let me not use an X. So there is a chaperone, and then the first van, say, has 2 spots for kids. But actually, I don't even want to do that because the hold on a second. Yeah, no, I do want to do that. So there are assigned seats in this van, of course. So it matters which kid sits where. If you don't believe that, then hang out with some kids and you will see that they have strong opinions about who sits where. And okay, so the first van is driven by a chaperone, and there are 2 kids. The next van is driven by a chaperone, and there are 3 spots for kids. And it does matter who sits where in that van. So let's just call those 3 spots. We might as well draw it linearly. And then the third van holds 4 passengers, not counting the driver. So vans, you don't typically think of the driver of a bus as being a passenger. Well, whatever. Passenger means, the other people that are not drivers. So the other van looks like this: a chaperone and 4 seats. Okay, so we have these 3 vans. We have these 3 chaperones. The 3 chaperones are driving the 3 vans, and we have a total of 9 spots. So there are only 7 kids in the class. So your first thought might be, oh, do we even really need 3 vans? Because we have just 7 kids. Can I just take these 2 vans? Nah, man, we do need the 3 chaperones. So the 3 chaperones are people too. They need to get to the swimming pool. And therefore, not breaking any kind of laws or anything of people sitting on laps and stuff. You really do need to take all 3 vans, because even if the kids are all so happy and friends with each other that they want to cram into the 2 vans, well, then the third chaperone is just going to drive this empty van to the swimming pool with no passengers in it, but they still have to get there somehow. Okay, so that clarifies why we really do need all 3 vans. But we don't really care. We're not really talking about the chaperones at this point. So there are these 3 chaperones, but here he says it is not a concern in this problem which chaperone drives which van. In other words, let's consider the 3 chaperones to all be indistinguishable from each other. Therefore, what we're really counting is the number of ways that the 7 kid passengers can place themselves into these 4, 5, 6, 7, 8, 9 spots. That's really the question, right? So, great. How many ways can they do it? Well, one of the ways, for example, would be if the 7 kids all crammed into the 3-person van and the 4-person van. If that's the case, then this van is empty. But now there are 7 factorial ways. I hope I did that right. I am somehow doubting myself now. 7 factorial divided by wait, what? Assume the 3 chapters. How many possible ways are there to transport the 7 students to the swimming pool using all the vans? Assume that the 3 chaperones are the drivers of the vans, so there's not a concern in this problem which chaperone drives which van. I take it back. Everything I've said was bad. A little bit of what I said was bad. It does matter. It doesn't matter who sits in what spot. If it mattered if we cared exactly who sat in which spot in the van, then this would be a trivial problem. Line up the 3 vans, label the first 2 seats in the 2-person van 1 and 2, label the next 3 distinct seats in van 3, 3, 4, 5, etc. And now we just have 9 spots. And all we need to do is 9 choose 7 to decide which 7 of those 9 spots will be filled with children, and then multiply by 7 factorial to permute them, otherwise known as 9p. What the hell am I doing? 9 times 8, but then times 7 factorial. Maybe I should have taken that break. This is like 9p7, right? Yeah. 9p7, which is just 9 factorial divided by 7 factorial. So, divided by 2 factorial, I mean. Okay, so, yeah. So, this would be the answer if it did matter which kid sat where. Okay, but it doesn't matter which kid sits where within the van. Okay, so this problem could have been written more clearly, to be honest, because how many different ways are there to transport the 7 students? What I now care about is which students are in which van, but now the order in which they sit within that van is irrelevant to me. So it's kind of like I have a clipboard and I'm keeping track of every kid and I want to make sure that I don't lose any kids or whatever. Then I need to sort of assign the kids to the vans. But once I assign the kids to the vans, hey, you 3 kids, you go to the 4-person van, then I don't actually even care or even pay attention to them once they're in the vehicle, like who sits in what order or whatever. That kids can figure that out amongst themselves. Okay, so now we see why this is kind of a hard problem, because here, why is this a hard problem? The reason it's a hard problem is because since you don't care the order in which the kids sit in the van, okay, so suppose you want to fill the 4-person van. Well, there are sort of 9 choose 4 ways to pick which 4 kids end up in that van. Okay, I might just have to give the answer to this problem, because I can't call up into my memory exactly the kinds of logic that students find sort of confusing. The thing is that there's sort of like these ghosts, right? There are going to be 2 children that are just kind of like not going on this trip, and you can think of them as kind of like ghosts, right? Let the empty seats in the van be filled with ghosts. And so you might say, in order to solve this problem in a non-casework way, if you're trying to be cool and not use casework, then this problem is really hard, and you're liable now to make a mistake. And the kind of thinking you might follow if you are attempting to do this problem efficiently is to say, okay, I got 9 spots, I have 7 kids, so let me think about there being like these ghosts or whatever. And now, let me do like a kind of multinomial or something, but then with ghosts. I need to distribute these 7 kids. I need to distribute the 7 kids and the 2 ghosts into the 3 vans somehow. The problem is that problem is, why is this not just an easy problem, you might think? Let me start with the solution, and then I'll maybe go back. So how I did this problem, the only way I could think to do it was to split this up into a bunch of casework. And the casework looks kind of like this. Option 1. The 2 spots in van 2 are unfilled. So that's what the X means. Okay, well that means that all 7 kids are going to cram into vans 3 and 4. I did not need such a big picture. Hold on, let me just make this a lot smaller. So here's the 2-person van, the 3-person van, and the 4-person van. Let's partition by the number of empty spots in the 3 vans. Look, either both empty spots can be in van 2, or both empty spots could be in van 3, or both empty spots could be in van 4, or there could be one empty spot in van 3 and 1 and 2 and 1 and 3, or 1 and 2 and 1 and 4, or 1 and 3 and 1 and 4. So by kind of tediously going through those 6 cases, now it becomes an easier problem. Because now I simply need to decide of my 7 kids, which 3 go into van 3 and which 3 go into van 4. And so this is just going to be 7 choose 3 ways to pick which 3 go into van 3. Here, this is just going to be 7 choose 2, or 7 choose... no, that's just wrong. Because there is... Okay. Because now there's... Maybe I should do it like this. So now there are 3 spots in van 3 and 4 in van 4. Here, 4 spots in van 3, in van 4, 1 in van 3, and 2 in van 2. Cha. And 1, 2, 3, 4. 1, 2, 3, 1, 2, 3. Maybe I did need more space. 1, 2, 1, 2, 3, 1, 1, and 2. Okay, so the red is the spaces where kids are going to go. So that, yeah, I agree with this, that there are 7 choose 3 ways of deciding which 3 kids go into van 3 and which 3 go into van 4. How about now? Well, now this is a multinomial problem, right? How many ways are there to send the kids to vans 2, 3, and 4? Well, I might as well line the 7 kids up in a row and pass out to them a little card that says you go to van 2, or you go to van 3, or you go to van 4. So I have 4 of these 4 cards, 1 of these 3 cards, and 2 of these 2 cards. And so I'm counting the number of possible strings of length 7, consisting of 2 2s, 1 3, and 4 4s. And so that is going to be 7 factorial divided by 2 factorial, 4 factorial. Okay, and now, how about now? Well, now I have a 2 spots in van 2, 3 spots in van 3, 2 spots in van 4. So now I'm passing out I'm making strings of length 7 consisting of 2 2s, 3 3s, and 2 4s. So that's going to be 7 factorial over 2 factorial, 3 factorial, 2 factorial. Okay, and now I somehow missed a whole little section here. Jump. Now, same kind of thing, but now it's 7 factorial over 2 factorial, 4 factorial. Again, using multinomial counting. Here, it's 7 factorial divided by 3 factorial, 3 factorial. And here, it's 7 factorial divided by 2 factorial, 2 factorial, 3 factorial. So, and then I just add them all up. That's it. So, okay. The analysis of this problem is not really complete until you talk about all the ways in which you could have gone wrong. But I'm kind of blanking on that a little bit now. What you want to do is somehow yeah. What you want to do, if you want to solve this problem using a multinomial counting theorem without casework, you're in trouble. Because you have now there are really 4 spots in van 4, 3 spots in van 3, and 2 spots in van 2. So if you're following this kind of note card analogy, then you have 2 note cards with 2s on them, 3 note cards with 3s on them, and 4 note cards with 4s on them. So you really do have 9 note cards. And so if you're distributing the 9 note cards to the 7 students, there's some kind of mismatch here. And so you might think, well, okay, let me think of there as being the 7 kids and then the 2 ghosts. So here's, kid 1, 2, 3, 4, 5, 6, 7, and here there are the 2 ghosts. And now what you're doing is you have your 9 numbers, and you're distributing your 9 cards out to the 9 people. And how many ways are there to do that? Well, that I can answer, right? If I have 7 kids and 2 ghosts, then I really can answer this problem. The answer is that there are 9 factorial divided by 2 factorial, 3 factorial, 4 factorial ways to assign the 7 students and the 2 ghosts to the 3 vans. And you might have even said that this was the right answer to this problem. But it's not the right answer to the problem. And the reason why it's not the right answer to the problem is because you're overcounting. There really aren't 2 ghosts. They're just 2 empty seats. And in other words, the 7 students are all distinguishable from each other, but the ghosts are not distinguishable from each other. So then you might be thinking, oh, I am very smart. I can handle this. Let me just divide by 2 to account for the fact that I'm overcounting. Because the 2 ghosts are just ghosts. They're sort of invisible entities. And so I shouldn't, if the 2 ghosts both end up in van 4, for example, then if the 2 ghosts both end up in van 4, then somehow I've overcounted because no, it's the other way around. It's like this. If 1 ghost ends up in van 3 and 1 ghost ends up in van 4, then if those ghosts were in fact children, then it would matter which child was in which van. But since they're just ghosts, and it doesn't matter which ghost is in which van, then you might think, oh, can I just divide by 2 or something? Because if the 2 ghosts swap places with each other, then who cares? The problem is that built into this supposedly efficient analysis with trying to place everyone, the 7 children and the 2 ghosts, into the 3 vans in sort of one step, you are also including, and now I'm going to kind of draw over this with a new color, the situation in which both ghosts end up in, say, van 4. Well, if both ghosts are in van 4, then I shouldn't divide by 2, because I'm not overcounting. That's really one situation in which the both ghosts have ended up in van 4. So whether or not the ghosts end up in the same van or different vans influences whether or not you have overcounted by a factor of 2 when treating the ghosts temporarily as people. Okay, and I don't know, maybe some very smart person is going to find a way that's more efficient than this just brute force casework, but this is the only way I could think to do it, and I don't think anyone has ever come up with kind of like a better way. All right, so that was not totally satisfying. All right, I think that was the last hard problem. Let's just finish this off because I got 3 problems left, 4 problems left. Let me just do this now in 5 minutes because this video is already 2 hours long or something outrageous like that. Let's go. DNA, and I think I'm only doing part B. DNA consists of 4 nucleotides, adenine, I guess you would pronounce it, cytosine, guanine, and thymine. The DNA strands AAG and AGA are considered to be distinct. Okay. Count the number of distinct DNA strands. This is straight multinomial. If it consists of 3 A's, 2 C's, 4 G's, and 2 T's, that's a 6, 7, 8. That's an 11. It's a string of length 11. And 3 of them must be A's, 2 of them must be C's, 4 of them must be G's, and 2 of them must be T's. And so, this is just going to be multinomial 3, 2, 4, 2. And thus the answer is 11, factorial divided by 3 factorial, 2 factorial, 4 factorial, 2 factorial. Okay, I don't think we need to say anything more about that. Let's keep going. A foreman has a team of 15 workers. Yeah. He needs 5 of them to unload a truck full of bricks. 3 to start mixing cement. Okay, so 5 are going to unload. 3 are going to mix cement. And 4 are going to clean up yesterday's mess. In how many ways can he create the work group? Well, the idea here is that there are 12 jobs to do, but we have 15 workers. So one kind of inefficient way to do this problem or something is to, well, it's not inefficient, it's perfectly fine. Just say, all right, well, first of all, there are 15 choose 12 ways to pick which of my 15 people will have a job at all. Now, having decided which 15 are going to have a job, then, well, I could be even more. Okay. Having decided now which 15 are going to have a job, having 15 total workers, 15 choose 12 ways of picking which 12 are going to have a job. Then, for every way there is to pick which 12 have a job, there are 12 choose 5 ways to pick which 5 are going to be unloading bricks. And for every way there is to do that, there are 7 choose 3 ways of picking which 3 are going to mix cement. And then there are 4 choose 4 ways to pick which ways to pick which 4 are going to clean up yesterday's mess. And okay, this is actually all the way back to the original way when we did multinomial counting. Maybe this is worth it to kind of revisit this. What do you get? You get 15 factorial over 12 factorial 3 factorial times, what is 12 choose 5? Well, it's 12 factorial over 5 factorial 7 factorial times 7 factorial over 3 factorial 4 factorial. And so you just get all this cancellation, right? The 12 factorials cancel, the 7 factorials cancel. And that's why the answer to this problem is 15 factorial over 3 factorial 5 factorial 3 factorial 4 factorial. And okay, of course, it was possible to do this very, very quickly if you realize that having no job is also kind of like a job, right? So really, if we have 15 workers, 3 of them are going to get assigned the job have no job. 5 of them are going to get assigned the job of unloading a truck full of bricks. 3 are going to get the job of mixing cement, and 4 are going to get the job of cleaning up the mess. And so therefore, this is really just a straight 15, 3, 5, 3, 4 multinomial counting, which is of course just this. Okay, 3 more. Oh my god. 12 children have been invited to Hitomi's birthday party. Okay. Her parents have bought 3 kinds of party favors for the guests. This is the dumbest problem ever written. I mean, just because okay. 3 pencil boards. I barely know what a pencil board is. In fact, I'm pretty sure I don't know what a pencil board is. But thank you, Gossett, for making me say the word pencil board. 4 colored pencils and sets, and 5 sets of colored marking pens. All right, so that's just confusing. In how many ways can the party favors be distributed to the guests? Well, we have 12. We have 12 party favors, and we have 12 children that have been invited to the party. So you might, without even thinking about it, just interpret this as a multinomial counting problem. And it really kind of is, right? If we have 12 children, then we might as well just line the 12 children up in a row and just distribute to those 12 children the 3 pencil boards, 4 colored pencil sets, and 5 colored marking pens. Well, now that's just asking how many strings are there of length 12 consisting of 3 of these, 4 of these, and 5 of these. And so that would be 12 factorial over 3 factorial, 4 factorial, 5 factorial. All right, I call this the nice Hitomi interpretation of the problem. In the world where Hitomi is nice, every kid gets a prize. But there is also evil Hitomi. Evil Hitomi invites children to her party, but to her birthday party. But you know, she's the birthday girl or whatever, so she is going to use her power to, like, you know, just ruthlessly take down certain children in her social circle in a kind of like Mean Girls sort of way, in which even though there are precisely 12 presents and there are precisely 12 children, who says every child must get a present at all? We could just give your best friend 5 presents and give a bunch of kids none. Ha 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 ha. And so, if there are no restrictions at all, then this becomes a complicated stars and bars problem. Because ultimately, look, I got these 3 pencil boards. Anyone can get these 3 pencil boards. In fact, I can even give all 3 pencil boards to one person, maybe. And then there I have my 4 colored pencil sets, and I can give those 4 colored pencil sets to whoever I want. There are no restrictions that says that every kid must get a present. I could give 2 of them to one person and 2 of them to another. Okay, so if there are full restrictions, then this is really like 3 independent problems. How many ways are there to distribute the pencil? How many ways are there to distribute the pencil boards? Well, you now think of the 12 children as being divided up into 12 categories with 11 vertical bars. And if I have 3 pencil boards, well, now I'm just distributing those 3 pencil boards in and amongst those 11 bars. So that's a string of length 14, and there are 14 choose 3 ways to distribute my 3 pencil boards to the 12 guests. For every way there is to distribute pencil boards, there I now have to count the number of ways there are to distribute the colored pencil sets. And now it's stars and bars again, but now there are 4 stars, right? And so it's going to be 11 bars separating the 12 children, plus 4 is 15. There's a string of length 15, and there are 15 choose 4 strings of length 15, consisting of 11 bars and 4 stars, and each one of those corresponds to a unique way of distributing the colored pencil sets. And 16 choose 5, because if I'm distributing the 5 colored marking pens, I now am dealing with 5 stars and 11 bars, so it's a string of length 16, and you multiply them because they're all totally independent of each other. Okay, oh my god, my brain is like fried. Last problem, which is number 31, is a 3-parter. Great. 6 government employees, including the president and vice president, are getting their picture taken for a newspaper column. And how many ways can the employees be lined up in a row for the picture if the president must stand next to the vice president? We did problems like this in pre-calc C even. If the president must stand next to the vice president, then just imagine them holding hands with each other. And now they're really not a separate person. They're really just a blob of president and vice president. Well, if there are 6 total people, but the president and the vice president are acting together as a unit, then there are just 5 factorial ways to permute those 5 things. The 5 things being the president and vice president blob, and then the 4 other employees who can move freely amongst themselves. And then I multiply by 2, because for each way there is to distinguish that, of course, the president and vice president can swap places. Part B, the president and the vice president cannot be situated on either end. Well, if the president and vice president cannot be situated on either end, then where must the president and vice president be? Well, somewhere in and amongst the 4 middle places. So let's first say that there are 4 choose 2 ways to pick from among the 4 middle spots, which 2 are going to be occupied by the president and vice president. Having chosen that, then there are 2 ways to decide, which order it is, whether it's president or vice president. Now that I've fixed the spots for the president and vice president, there are then 4 factorial ways to distribute the remaining 4 government employees to the 4 remaining spots. Okay, and finally we're on part C now. There must be at least 2 employees between the president and vice president. Make a table to help solve this part. Okay, this is kind of a callback to the very first problem from this video. I don't feel like talking about multiple ways to solve this. I'm just going to solve this in one freaking way. And the one way is just with cases. If there must be 2 spots in between the president and vice president, then let's first go through the case where the leftmost spot is occupied by the president or the vice president. Well, then there must be 2 spaces, and then Well, potentially the fourth spot could be occupied by president or vice president. Or if the president was sitting in the first spot, there could be, then it could be the fifth spot, or it could be the sixth spot. So these are the only three possibilities, assuming there's a president or vice president in the first spot. If there isn't a vice president in the first president or vice president in the first spot, then there might be a president or vice president in the second spot. Well, if so, then there can't be a president or vice president in spots 2 or 3. So perhaps there's one in spot in spots 3 or 4. There might be one in spot 5, or there might not be. Those are the only two possibilities. And then finally, if there isn't a vice president in spot 1 or 2, then perhaps there is one in spot 3. And if there's one in spot 3, then there can't be one in spot 4 or 5. There must be one in spot 6. And now I've exhausted all the possibilities because you can't have spots 1, 2, and 3 taken up by a non-president or vice president, because then there would be only 3 spots left for the president and vice president, and they would not be able to be 2 apart from each other anymore. Therefore, these are the 6 total possibilities, and therefore there are 6 ways to do this. And for each one of these formations, there are 2 ways for the president and vice president to trade places with each other. And then there are 4 factorial ways. Then there are 4. I guess there are better way to say it is there are 2 ways to decide which of the X's is president and which is vice president. And then there are 4 factorial ways to fill in the remaining 4 government employees. Having now done this, I mean, it really is quite tempting to now do a more sophisticated analysis where we sort of say, we basically make a, how do we do this? We basically make a P/VP blank tile and a PVP tile. And we do kind of what we did before, right? Which is we stars and bars it now, and we say, okay, PVP blank blank, I should say, because there have to be in fact 2 government employees in between the president and the vice president, the leftmost one and the rightmost one. And so now you're sort of saying, okay, if that's been decided, now there are I'm free to distribute the 2 remaining government employees can go kind of over here to the left of the president, vice president, whoever comes first, or here or here. And so this is now a stars and bars problem in which, feel free to distribute the stars however you want into the 3 places. And so there are, if I'm doing this correctly, now thinking of the PVP as PVP blank blank tile as a bar and the other PVP one as a bar, I now have 5 choose 2 ways. I hope I'm not messing up. 5 choose 2 ways to, but 5 choose 2 is like too big or something, right? That's 10? Yikes. What am I doing wrong? Oh, because it's not 5 choose 2, it's 4 choose 2. I have 2 bars and 2 stars, and so there are 4 choose 2. So this is the way to avoid casework. I'm smarter than you, Gossett. I don't need to make a table. There are 4 choose 2 ways. This is a complete callback to the very first problem in this homework that we did 7 ways. Here I'm going to do it just 2 ways. Brute force chart, and now there are 4 choose 2 ways to make strings of length 4 consisting of 2 bars and 2 stars. I interpret the stars as extra spots for low-ranking government employees, and I interpret the 2 bars separately. I interpret the first bar as, I think you guys get it. So this is, of course, 6, and now I've sort of, using a counting principle, I have now determined that there are, in fact, 6 sort of formations, because what I've now decided is precisely how many low-ranking government employees will be in the spots before the first president, vice president, spots in between them, and spots after them. And by adding 2 blanks to the tile here, I've sort of forced there to be at least 2 in between the left one and the right one. Okay, and then the rest of the problem just solves itself, right? Then I still have two ways to decide who goes first, president or vice president, and there are still 4 factorial ways to fill in the 4 low-ranking employees into the 4 low-ranking employee spots. But how many low-ranking employees occur in the 3 different areas, I have determined via kind of a counting principle that would continue to be a reasonable way to solve this problem, even if the numbers were much larger. So I feel better about myself now. Okay, I'm shocked to know how long this video ends up being. That was a very thorough and pretty decent review of every single one of these counting problems from this second section. Hopefully you are like an expert on counting now. Goodbye, everybody. Sorry for this video being 9 days later than it should have been.